I'd like to welcome everybody to February Flare Up Week 3. I'm Karen and I'm coming to you from Treaty 6 territory. Treaty 6 is located, I'm located in Leduc, Alberta. So Treaty 6 encompasses a large landmass and was the traditional lands of many Indigenous peoples, including the Cree, Dene, Blackfoot, Saulteaux, Nakota Sioux, and Métis people. I think it's important to note that land acknowledgements are great, but reconciliation is more than just that. It's an ongoing process that requires learning, reflection, and action to build respectful relationships between Indigenous and non-Indigenous communities and the many places and spaces in which we meet. So I'd like to welcome you all to week 3. I'm really excited for this session. We have 4 different projects, so it's going to be a bit longer. We're heading into 2 hours here. But we're going to feature 4 projects from the NSERC network from across Canada. And today we're going to kick it off with Max. Max is a master's student from the University of Toronto, and he's going to be talking to us about optimizing air tanker dispatch policies for forest control. Before I hand it over to Max, just to let everyone know, our process for these sessions is a presentation followed by a live question and answer or discussion period. So should you have any questions, please feel free to post them in the chat box and we'll do our best to get to them in between the sessions. So welcome, Max. I'll hand it off to you.
Okay, yeah, thanks. Can you hear me all right?
Yeah, you're great.
Okay, sweet. Thanks for the intro, Karen. So yeah, my name is Max. I'll be presenting my project here, Optimizing Air Tanker Dispatch Policies for Forest Fire Control. I'm a second-year master's student at U of T, and I'm supervised by Professors Vahid Sarhanjian and David Martel. Okay, yeah, so I think I don't need to convince this audience that wildfires are becoming more frequent, intense, and destructive. Here's an image from last year. Western Canada had a bad year. This particular image is from Manitoba. And then here are some alarming statistics or projections for wildfire and how it's going to become an even bigger problem in the future. And it is a problem now. And here's another image from Jasper 2 summers ago in 2024. Um, and so an important component of forest fire fighting is air tankers, and they support the initial attack phase when the focus is on containing fires. They drop water on fires, right? And the key though is with forest fires is not all of them actually require air tanker support because fire differ in their risk level, and risk is kind of we determine risk with things like proximity to valuable resources, potential to spread, and the size of the fire. Um, and what's difficult about the decision of when to dispatch air tankers is they're made in real time and they're made under uncertainty concerning the number, behavior, and risk of future fires. So you don't know what the rest of the fire day is going to look like when you're trying to make a dispatch decision. And then another thing with forest fires is the demand can often exceed the supply of air tankers. You might not be able to fight every fire that you want to fight. So there's an interesting optimization problem kind of emerges here. So the objective today for this talk is, well, the overarching goal is to support better air tanker dispatch decisions under uncertainty. So first, I'm going to introduce our simulation model, which we use to simulate real fire season days. So we simulate or model fire arrivals and then also the air tanker service process. And we're using data from the Sudbury area, Sudbury in Ontario. So yeah, we're gonna be comparing different air tanker dispatch policies and evaluating how well they perform. We're going to use, I'll talk more about what an MDP is, but we're going to use a Markov decision process framework to obtain an approximately optimal dispatch policy. And we'll highlight trade-offs between simple, intuitive rules and more complex decision strategies. So first, let's talk about the model. So the first step is we're building a model that's trying to represent real air tanker operations reasonably well. Our fires are going to be treated as our jobs or customers that we're trying to serve, and then the air tankers are treated as the limited resource server that's serving those customers or jobs. So if you look at this diagram here, we have this. Can you guys see my mouse, by the way? Yes.
Yes, we can.
Sweet. Okay. So yeah, if you look at this diagram here, we have this base in Sudbury, Ontario. It's equipped with some number of air tankers. Here there are 3 air tankers, and it's serving a service region with a radius of 250 kilometers. For us, we actually divide this service region into cells of 20 by 20 kilometers. And then so fires don't actually appear in specific, like they don't have like a lat and long. They just appear in a cell. And there's roughly 350 cells in this area. So more on the actual fires. So as I said earlier, fires are detected and reported throughout the day. They're not reported all at once. So when the RDO, the regional duty officer, is making a dispatch decision at say 1 p.m., they don't know if and when future fires may be reported. And then each of these fires are going to be classified into some risk category. And that risk is going to, for us, is going to be based on 2 things. So first is WUI, which aims to show like the fire's proximity to valuable resources. And then there's the ISI, which represents the fire's spread potential. So if you look at this diagram here, there's two high risk fires, and then with the red symbol there, and then the three low risk fires. So, and then another key with the fires is we're using a model from Melanie Wheatley to determine the probability each of these fires actually requires an air tanker, because I mentioned that not every fire gets an air tanker. Okay, yeah, so now let's talk about the air tanker service process. So the air tanker is going to go through three service phases. In this diagram here, you can see one air tanker is on the way to a fire, one air tanker is on scene with a fire, and one air tanker is returning back to base. So those are the three phases it progresses through. The model, again, does not track the exact location of where the air tanker is. It doesn't know the lat and long of the air tanker, but it knows what phase of service we're in. And the travel times obviously will depend on the distance, and there's also a randomness component in there. And then the on-scene time for us doesn't, it varies. There's randomness, but it's not going to depend on fire location or risk level or distance to lake, any of those factors. It's exogenous from all that stuff. Um, and another important thing to note here is for us, when air tankers are dispatched, they cannot be diverted to another fire before returning to base. So for this air tanker, it's sent to this fire. It's got to return back to base before it can be dispatched again. Okay, so on dispatch decisions in our model, dispatcher decisions are being made, they've been discretized, they're made every 30 minutes. And at each decision point, we consider all active unserved fires. So in this diagram, we have these three fires that do not have an air tanker assigned to them yet. So they would be our three dispatch options. But we have this fourth dispatch option, which we call our do nothing now or our do nothing option. And that would be, you're choosing to keep the air tanker back in anticipation of future demand. So we'll talk about this more later, but maybe that's sometimes the best decision to make. And for us in our model, we're restricting dispatch decisions to the daytime operations, which for us will be between 11 a.m. and 7 p.m. Okay, so those are like the basics of the model. Now, what are we trying to actually optimize? And in this case, we're trying to minimize a total waiting cost. So, oh wait, sorry, I think I skipped over a slide. Yeah, okay. So first, I want to talk about all of the performance measures we care about. So the three that we care about, I guess I just alluded to one of them. So the first one's going to be total waiting costs across fires, and we'll define what that means. And then we're also going to look at average response time and the number of fires left in the queue at the end of the day. Those last two statistics will be compared across risk types, so we can see what maybe some policies are better at responding to high risk fires or low risk fires. And just a small note, some fires are not going to be receiving air tanker support, but they're still going to be included in performance measures. We have a way for accounting for that. So yeah, on this idea of total waiting costs. So when a fire is waiting for air tanker service, it's accumulating costs. The longer a fire waits, the more damage it may cause, and thus the more cost it should incur. Cost is going to increase faster over time. We have a quadratic cost function, and I'll have a few diagrams to show what that means. And so obviously higher risk fires should be accumulating costs at a faster rate. And this will create trade-offs where even if, let's say a high-risk fire arrives after a low-risk fire, it might actually be a higher priority than that low-risk fire. I'm not going to spend too much time talking about the data that we're using, but we're using real data that was provided to us by the Ontario Ministry of Natural Resources. And we're using several models as tools in our own model, including models from Doug Wolford, Mike Waddington, Dave Martell, Nick Clark, and Melody Wheatley. So yeah, now that we have all of our like model basics covered, let's talk about the different policies that we're going to be comparing in our simulation. So the first policy is called our generalized CMU policy. So with this policy, at every decision point, you're going to look at all of your active unserved fires, and you're going to assign some kind of priority score to every one of those fires. And then you're just going to dispatch your air tanker to the fire with the highest priority. So intuitively, high-risk fires should matter more. Fires that have been waiting longer should matter more. And then also quick wins should be attractive. So if you project that a fire will only take an hour to serve, and there's another fire that might take 2 hours to serve, you'd want to prioritize the fire that's quicker to serve. In this diagram here, you can see there are two different fires, and they each will be given a priority score. And the key with this CMU policy is that it's greedy. So if an air tanker is available, it's always going to dispatch an air tanker. So it's never going to choose to do nothing. It's kind of myopic in that it looks at the current state, it finds the fire with the highest priority, and it dispatches. So why might this policy not be optimal? So consider a situation with one active low-risk fire far away from Sudbury. Well, this CMU policy, and sorry, just a note here, but the policy has the C, which represents cost, and then mu is service time. So that's those are the two main components that inform this policy. Anyway, in this situation, the CMU policy would dispatch, right? Because it only sees one fire, and that fire will thus have to have the highest priority, and it's going to dispatch to that fire. But what if we wait? So let's look at this situation here where, again, there's a low risk fire far away from Sudbury at 1 p.m. Well, the CMU policy sees that fire. It's going to dispatch the air tanker to that fire. And then let's say we skip ahead to 2 p.m. and a high risk fire pops up way out east over here. Well, now we're exposed and vulnerable to that fire, right? So there are situations where the CMU policy would not perform well. So to address this issue, we're going to introduce a framework called Markov decision processes. So the idea here is we want our decisions now will affect what's possible later. So we need to balance current fires against possible future fires. And the MDP framework allows us to do that. So we're making forward-looking decisions. And at each decision point, we look at the current state, we look at where our fires are, we consider all of our feasible actions, so all of our dispatch options. We account for uncertainty about future fire arrivals, and we use that cost function that I defined earlier to help understand what good and bad actions are. And then we're going to choose the action that minimizes the expected future cost of those different actions. So in short, what this policy allows us to do is it allows our decisions to consider what might happen in the next hour, 2 hours, and so on. So a good analogy or a good example would be chess, right? So when you're playing chess, you don't want to make a move based solely on the current board. You want to make a move that puts you in the best position to win. And the best chess players are able to see like 1, 2, 3, 4, however many moves in the future, right? So what's difficult about that is a human decision maker can only consider so many future responses or future possibilities. So that's why we were seeing robots like Deep Blue or AlphaGo is a robot that beat a human operator in the game of Go, but Deep Blue beat a human operator in the game of chess because the computer has the ability to see, well, theoretically, all the way in the future, right? But a human can only see so far ahead in the future or consider so many possible future possibilities. So with this example of chess, it's kind of similar to dispatching air tankers, right? You want to look in the future and balance whether it's better to prioritize the fires that you have right now or prioritize those fires that might be popping up in the future. So the problem with this MDP framework, though, is the number of possible future fire scenarios is enormous. And because the reason for that is because fire arrivals are random and there are many possible fire locations and times. So the number of possible future scenarios is just way too large for even a computer to handle. So we need an approximate way to solve this problem. So now I'm going to introduce our second policy. So we had the CMU policy, and now I'm going to introduce the hindsight policy, where, again, at every decision point, we're considering all of our active fires, but we're also going to consider this new option of doing nothing. And for each of these possible actions, we're simulating many possible future fire scenarios that evolve after making that particular action. So the same way that a chess player is thinking, if I move here, what might happen in the future? That's what this MDP is also going to be doing as well. And then you're going to estimate the expected performance of each of one of your action options, and then you'll select the action with the best expected outcome. So this policy is forward-looking. It takes into account the possibility of future fire arrivals. Okay, so now that I've talked about our two policies that we compare, I'm going to just talk about the experiment we ran, the experiment setup. So we ran experiments where we're varying the number of expected fires in the day. So we have these three numbers, 15, 30, and 45 expected fires. They're supposed to represent a busy, a very busy, and an extremely busy fire day. And for each of these fire days, we're running 2,500 trials. So the trial will simulate fire arrivals and air tanker service process and so on. We're going to do that for each policy and then just compare their performance according to those cost functions that we defined earlier. So now I'll talk about the results. So with this first graph here, you'll see on the x-axis, we have 15, 30, and 45 fires, again, representing busy, very busy, and extremely busy fire days. And we're looking at the relative improvement of the hindsight policy over the CMU policy. So along the y-axis, you see a cost reduction title there. With the 15 expected number of fires, we're only seeing a marginal improvement of the hindsight policy over the CMU policy of roughly 1.5%. But then once we move to these very busy and extremely busy fire days, we're seeing improvements that range from, let's say, 7 to 9%. And so now let's look at some other graphs to understand why is the hindsight policy outperforming the CMU policy. So this next graph here, what we're looking at is the response time by risk level. So these orange bars represent the hindsight policy and the blue bars represent the CMU policy. And we're looking at how well do these different policies respond to our low risk fires and our high risk fires. So you'll actually notice that for low risk fires, the hindsight policy is doing a better job the CMU policy is doing a better job of responding to them. It's getting to those low risk fires quicker. But for the high risk fires, the hindsight policy is outperforming the CMU policy. And it's the same, we see the same story when we look at the how many fires are left in the queue at the end of the day, again, sorted out by risk level. So more fires are served by the CMU policy. There are fewer fires in the queue at the end of the day with the CMU policy, but there are more high risk fires in the queue at the end of the day with the CMU policy. So the same story, we're seeing the same story there, right? The hindsight policy is doing a better job of responding to high risk fires and doing a worse job at responding to low risk fires. So let's look at this other plot. So we were kind of curious, how often or how does the hindsight policy allows for the do nothing option, right? And how often is it making that do nothing option by time of day? So along the y-axis or along the x-axis here, you see it's about from 12 to 7 p.m. And along the x-axis, this should say dispatch rate. How often are we dispatching? And then I guess the inverse of that would be how often are we doing nothing? So when we're looking at a specific case here where we're down to our last air tanker and there's some active unserved fire. And we're seeing how often are we dispatching to that active unserved fire. So you'll notice and also just note that this axis ranges from like 65 to 100%. So we're seeing that in the early afternoon between, let's say, 1 and 3 p.m., there's this dip in dispatch rate. And that's actually aligned with what we see in our hourly fire arrival probabilities. As some of you may know, there's like a peak in the early afternoon for when fires are being reported. So what's happening here is the hindsight policy is seeing at 1 p.m., well, maybe there's a fire active, but I know that there's a good chance another more dangerous, riskier fire might arrive in the near future. So it's more important to be a little bit more conservative at this time of day. But then as you move into the late afternoon, roughly around 4 to 7 p.m., that dispatch rate goes up to 100%. So what it's seeing there is there's actually a low probability that another fire, a more dangerous fire, might arrive in the near future. So it's best to just send the air tanker to the active fire that you know has already arrived. So here's just a quick summary of the CMU and hindsight policy. So the CMU policy, it's simple and intuitive. It's easy to explain and justify. We actually saw it performs well when the need for air tankers and the supply of air tankers is roughly equal. So on these busy days, it's doing pretty well. But and its defining characteristic is that it's always dispatching an air tanker to the highest rated fire at the time of decision, right? It's never choosing to do nothing. The hindsight policy, it's more strategic and forward-looking. It's better, as we saw, at reserving air tankers for high-risk fires. It does a better job at responding to high-risk fires because it explicitly accounts for future uncertainty. And its defining characteristic relative to the CMU policy is that it may choose to do nothing. So just to wrap up, why is our work important? So these strategic policies, like the hindsight policy, become especially valuable in some situations. So like we saw these very busy fire days, it might be important to use these more strategic policies, because the biggest differences in these policies appear when resources are scarce, which will probably become more common in the future, right? There might be these very busy fire days might become more common, and we might not necessarily have the resources to match that demand. And these are precisely the situations where the dispatch decisions are most difficult. So moving forward, our goal, again, is we have this overarching goal of supporting evidence-based decision-making in Ontario. We want to identify when these strategic dispatch rules truly outperform simpler ones. And, we kind of have this hope that maybe we can help train new decision makers in Ontario, help them build an intuition for when it's best to actually do nothing. Try to understand try to build an intuition for when those decisions are optimal. And I think that's all I have for my presentation. Thank you.
Awesome. Thanks, Max. And thanks for hopping back into it there. I know it can be hard to hop back in after technical difficulties. You did a great job.
Thank you.
Super interesting stuff. I always find this really fascinating, and it almost rings to me kind of like economic analysis in a lot of ways, right? The intricacies of the models being run out of the lab that you're from are astounding to me. So we have a question in the chat. Oh, I'm just trying to get all of the emojis to disappear. Okay, so one of your performance measures was an average of something. Averages can hide important bad cases of long delays. Is there a potential to use something like an 80th percentile in place of an average?
Yeah, that's helpful feedback because you're right that all of our performance measures are just looking at averages. We're putting confidence intervals on where we think that average is. But if it's important in practice to avoid those situations where, let's say, the response time is very large, then yeah, that's helpful feedback. But yeah, right now we're not necessarily tracking how often does it take more than 4 hours to respond to a fire. We're not explicitly recording that right now, but that's easy enough to record, and it's helpful to know that that might be like useful information for people.
Awesome. Thanks, Max. And looks like a good contact there for you to reach out to with Ontario. All right. I'm getting my computer's about to die because apparently I failed to plug it in properly. Warning. There we go. Okay. So are there times when dispatching all three tankers to one fire could be the best decision?
Yeah, so maybe there are going to be fires that are like all hands on deck type of fires. So we're interested in cases where like there's an optimization problem, but for like those types of fires where like it's send all air tankers to that fire because maybe it's threatening a community or something. There isn't really like an optimization problem there. So like we don't account for that situation, but I guess in between that is like maybe fires that are very dangerous or very risky. Like you want to send two air tankers to that fire. Our model doesn't actually, we don't have that dispatch option. It is just send one air tanker. And actually for our purposes, we kind of say that these we have two air tankers bolted together because I guess it's in practice, oftentimes you do send two air tankers to a fire. But anyway, the point is like there are going to be cases where maybe you want to send maybe 50% of your resources to a fire. Well, yeah, for us, we're not accounting for that. I hope that answers your question, but I guess there's those cases where there's like very, very risky, dangerous fires that you want to send all your resources to. But we don't really, that's not really an optimization problem. Um, but in between where we are and where those extreme fires are, yeah, like there's room for us to improve, but right now we don't account for those types of situations.
Thanks, Max. And I think you brought up a good point there that correct me if I'm wrong, we're talking about ground refilled like air tankers filled with, I'm assuming,
Yeah.
retardant. Um, we're not talking like tanker groups that are skimming or something like that. We're talking,
Right.
am I correct?
Yeah. They return back to base, they refuel, the pilots prepare for their next dispatch. But yeah, so they go out to the fire and they return back.
Okay. And are they having to land to like to be filled each time, or are we talking about ones that can skim as well?
Yeah, so the air tankers in Ontario, from what I understand, are picking up water at nearby lakes, right? Because Ontario has a lot of lakes to pick up water from. So I think when they come back to base, yeah, the pilot's just kind of resetting and they're refueling if necessary. Um, yeah, that's my understanding of
Okay.
the
Okay,
operation in
cool.
Ontario.
Yeah, and it's interesting to note that it's different across Canada. So Ontario has lots of lakes, and that works great. And then you come to some areas in Alberta where I am, and that might not be an option in a lot of areas because there actually aren't water bodies close enough that are large enough to do those kinds of operations.
Right.
I have one more question here. So in the future, do you see the possibility of incorporating ground crew resources and location into this kind of model?
Yeah, so that would be awesome because like I was talking to a regional duty officer here in Ontario last February, and he told me, one of the most important factors that goes into his dispatch decisions is where his crews are, right? Because you want to protect the people, right, that are on the ground. Um, so yeah, no, our model doesn't account for that right now, and that would add a whole other. So as I mentioned with MDPs, like these problems blow up very quickly when there are just the computer can only enumerate so much, and you add more factors, the model becomes more complicated. So right now, I guess we're starting with what we think are the most important components of this model. But yeah, in the future, it would be great to have a lot. It would be great to incorporate the location of where your crews are, right? Because that is obviously an important factor in what goes into making these dispatch decisions.
Awesome. Thanks, Max. And while I'm chatting, Mike, if you want to pull up your slide. So there's just, I think, a nice comment here in the chat with a friendly suggestion about terminology and that do nothing can sometimes grate in the fire response culture. And they suggest kind
Hmm.
of a fun, cheeky term instead. Does the term like wait for worse make more sense in your model?
Yeah,
So
I
not,
mean that's what we're doing, right? So that works too.
yeah.
Yeah,
Well, great
yeah,
job, Max.
yeah, I agree. Do nothing kind of has a connotation to it, right? But
Yeah.
um, yeah, we'll think about that. That's helpful.
Awesome. Well, thanks, Max. That was a great presentation. And just so everyone's aware, we're hoping to have a little bit of time at the very end of the session. So if you still have questions for Max that we haven't gotten to, feel free to post them in the chat box and we'll do our best to get to them then. Okay, so we're going to hop into our second session here. We're going to have Mike Waddington, who is a network PI, and Owen, a postdoctoral fellow from McMaster University. And they're going to be talking to us about peat fires and changing climate. So welcome, Mike and Owen.
Great. Thank you. Can everyone hear me okay?
Yeah, you're great. I'll hand it off to you.
We're going to talk a little bit about peat fires in a changing climate. And this is a pretty intriguing question because this is what a peatland looks like. These are generally very wet ecosystems that may have a porosity of 90%. And so they're mostly water, but they also have a lot of organic matter, which acts as a fuel. And you can go from a situation like this to a situation like this, which can be quite problematic. This is the Tomahawk fire in Alberta. This is 11 months after ignition, and we still have large amounts of smoldering combustion. Now, this is a drained peatland, and I'll come back to that a little bit later. But we can think of these ecosystems or these across the landscape as acting as a fire break. Here we have a situation where the peatland you can see there is unburned. Sorry, it's the peat is loose. It's mostly water, so it has very little fuel if it were to ignite, and it has a lot of water that has to be driven off for ignition. But we also can have situations like this where if the peat is dry and dense, that it actually can act as a fire propagator, linking different components of the landscape and helping a fire propagate across the landscape. Now, if we look within a peatland itself, we can have both of these situations occurring. Generally, in the middle of the peatland, which is a figure on the left, we can have a little bit of combustion, but for the most part, we're only losing about 1 kilogram of carbon per meter squared per fire. Just skims off the first few centimeters of depth of burn. But at the margins of these peatlands in Alberta in particular, we can have 5 to 20 times the combustion in the middle. And the reason for this is that the edges of this ecosystem are drier. Because they're drier, the peat becomes denser, and then we end up with a lot more depth of burn. Now, why this is important is we need to try to figure out where the thresholds are between these two states, from resistant to a vulnerable state. And we studied the Parry Sound 33 fire, and what we have here is a plot of percent of the profile that burned as a function of the peat depth at a variety of different plots. And I've plotted showing here are the margins in the middles of the peatland. What's really important to note here is that using a breakpoint analysis, that we can see that greater than a depth of about 60 centimeters, that you have very little depth of burn. And what was really valuable about this fire is that we have monitoring a lot of sites adjacent to the fire, and including one within the fire itself. And if we look here at the water table depth within the peatland on the ignition date on the y-axis as a function of the maximum peat depth of that peatland, and go to that same breakpoint, all the sites, all the peatlands that were shallower than that breakpoint had no water table. The peatland was completely desaturated. And so we see that increase in the vulnerability. And Owen will talk about why that's really important for our modeling work a little bit later. So this is really critical for establishing thresholds to burn severity. And why this is really important is that peatlands are going to become drier under climate change. In fact, they're going to dry at a greater rate than forests. It's a paper we published in Nature Climate Change. And essentially it describes this positive feedback system where as CO2 concentrations in the atmosphere increase, we get increased in temperatures. That increases the vapor pressure deficit, which increases evapotranspiration. That drops the water table in these peatlands, which results in a drying or lowering of the volumetric moisture content. And then that sets off a variety of mechanisms, which most importantly are increasing the peat burn rate and the peat burn severity, i.e. the depth of burn or the amount of combustion, smoldering combustion in these peatlands. And this is a really tricky question or approach to be able to quantify the effect of climate change on the increased burn rate and severity. To look at this, so there's two approaches that we can take. One, we can do a field experiment where we go to a site which has been drained, where the water table has been deliberately lowered, and to mimic a future climate change scenario, or we can do some modeling. I want to talk a little bit about the field experiment approach. And some of you may have seen this before, but we were given a really good opportunity from the Fort McMurray fire in 2016, in that in the middle of the highway south of the city, there was a drained peatland. And this is a site where they put in drainage ditches to lower the water table in that peatland. So it gave us 3 locations where we could quantify combustion: undrained, moderately drained, and heavily drained. And when we look at what those systems look like, here's the undrained site. This looks very similar to that figure I showed you earlier. We see sites where there was no combustion of the peat. When you can contrast with the heavily drained site, and you actually see evidence of the mineral soil, where the organic soil has combusted right down to the underlying mineral soil. And we look at the depth of burn on the y-axis versus different treatments: undrained, moderately drained, and heavily drained. We see a significant increase with each of those sets of drying. So this suggests that, under climate change with increase in drying, that we're going to dramatically increase burn severity. And I should point out here, we actually have values burning right down to the bottom of the peat profile. When we quantify that as a carbon loss, and I'll draw your attention to the black bars first, the undrained site loses about 1 kilogram of carbon per meter squared, which is what we see quite commonly across the middles of these peatlands. That increases to about 3, but then over 20 kilograms of carbon per meter squared. And that sounds like a lot of carbon, but when we express that as the percentage of the carbon that had stored in this system over 6,500 years of development, we're losing about half of it in that combustion component, which is really quite concerning. Now, I should point out that by choosing a drained site as an analog for climate change, it's the worst case, most pessimistic scenario, because peatlands have built-in regulatory mechanisms that can hold on to their water during longer-term drying. So to really get at the climate change scenario, we really need to go with a modeling approach. And Owen will take over now and show some of our more exciting recent findings there.
Thanks, Mike. So as Mike has explained, field experiments have been a really valuable source of process-based knowledge on the interaction between peatlands and wildfire. But as we get more interested in projecting the integrity of peatlands and their carbon stock into the future over decades and centuries, we really need to make use of models. Modeling the future losses to smoldering combustion due to climate change has been something we've been working on over the last year. And there's a number of ways to project the depth of burn to smoldering. One method that's been previously used successfully is an energy balance approach, where you roughly quantify the energy released from combustion and you compare it against the energy that's required for ignition and further propagation of the smoldering front. And you can see an example of that approach in the bottom right figure, where peat that is vulnerable to smoldering has a ratio of H combustion to H ignition over 1. I'm just trying to change the slide, and I was hoping to take control of Mike's computer, but it doesn't seem to be cooperating. So for this present work, we've actually opted to use a different method to estimate the potential depth of burn. When the upward water flow from the water table can no longer meet evaporative demand, the water content falls and surface soil water tension rises, a quite pronounced increase. Previous ecohydrological research has demonstrated that there is quite a profound threshold that exists in sphagnum-dominated peatlands, where at a tension of around 100 hectopascals, we observe a host of severe ecohydrological consequences. And the most concerning of those from a combustion standpoint is the onset of desiccation in sphagnum mosses, which means it is much more susceptible to burning. It looked like it worked that time. This isn't a process that exclusively affects the surface. As water content falls and soil water tension rises deeper in the peat profile, those soils also become vulnerable to burning. And in order to estimate future smoldering potential, we needed to relate the critical smoldering threshold of 100 hectopascals to the water table position. And to accomplish this, we used Hydrus 1D, which is a one-dimensional soil moisture dynamics model. And we ran the model with a variety of evaporation rates and water table positions until we reached an approximately steady state moisture profile. And then we equated the depth of the 100 hectopascal threshold with the potential depth of burn. And in this table, you can see the minimum water table depth required before smoldering propagation will occur under a variety of evaporation rates. Basically, what we're seeing here is that under greater evaporation, the minimum water table needed to allow smoldering to occur becomes shallower, meaning the water table is closer to the surface, and the peatland as a whole becomes more vulnerable to burning. Projected climate change is going to alter both the peatland water table and the evaporative demand, and so this in turn is going to alter potential smoldering carbon loss. Under our contemporary climate, as Mike mentioned, bogs typically release 1 or 2 kilograms of carbon per meter squared during combustion. But as we get drier, we go to 10% and 20% lower precipitation. I cannot go backwards. When we get to 20% lower precipitation, we can see that bog smoldering loss increases even without an associated increase in temperature. This can easily cause a doubling or even quadrupling of smoldering loss relative to our current climate. When the temperature that's associated with climate change is considered, so here we have the baseline condition at 0. When we go to 2 degrees Celsius and 6 degrees Celsius, there are further increases in the smoldering losses due to the higher evaporative demand. Now, in contrast, fens will go from virtually no combustion loss under a contemporary or wetter climate to very strong increases when precipitation is decreased and temperature is simultaneously increased. And this suggests that the burn severity and area burned of fens could increase in the future in some parts of the world. But the effects of climate change are not evenly distributed around the globe, particularly associated with the patterns of precipitation, which are notoriously heterogeneous. But we're confident that some places are going to get wetter and others are going to get drier. And since we're interested in estimating the future global change in peatland combustion losses, we needed to explicitly consider the spatial patterns, and not just of climate change, but also in the distribution of peatlands and the distribution of wildfire. So the boreal and subarctic regions of the Northern Hemisphere are where we find the greatest extent of peatlands. Canada's boreal, the Hudson Bay lowlands, and the Siberian lowlands have the highest peatland coverage. And if we look at the patterns of wildfire, we do see some co-occurrence where we have both high fire frequency and high peatland coverage. And this is particularly in the circumboreal region in North America and Eurasia. And these are the spots where we see lots of peat fires today. We performed some random forest modeling to predict average burn frequency. We modeled fires in North America and Eurasia reasonably well. You can see North America in the figure on the left and Eurasia in the figure on the right. The model struggles a bit in areas dominated by small fires, so in sort of bottom left-hand quadrant of these figures. But in the boreal biome, where most of the peatlands are, large fires are common, and so we don't think that this is going to be a big source of error for our analysis. The random forest model used climatic moisture index as one of its predictors, and this allowed us to project the future area burned under a variety of climate change projections, which are represented by the shared socioeconomic pathways, or SSPs. So when we combine all of these disparate pieces of information and models, and it's kind of a bit of a Frankenstein, but when we look at the end of century, so 2100, we can see that peat smoldering losses are going to be 40% higher under the modest climate change associated with SSP 2-4.5. And we project up to 70% higher under the more pessimistic SSP 3-7.0 and SSP 5-8.5. And much of this increase is going to come from North America and more specifically Canada. Eurasian contributions to peat smoldering losses stay between 5 and 7 megatons of carbon per year, regardless of the time period and the specific SSP. Now you'll note the rather large error bars associated with these projections, and that is the standard deviation that's associated with different general circulation models, which we used. So what we're showing here is an ensemble mean, but the large error bars indicate that there are some differences between the different climate models. So when we look at the projections spatially, we can clearly see the regional differences between North America and Eurasia. The Canadian Western Boreal and Siberian lowlands will experience an intensification of their already high peatland carbon loss. But there's other emerging areas of concern. So, pardon me, Silesia in Eastern Europe will be the site of large peatland carbon loss in the future. And the Hudson Bay lowlands, which is the second largest contiguous peatland complex in the world, and which historically has had very low fire frequency, is going to experience far, far greater carbon loss in the future than it currently does. And as one of the most significant terrestrial carbon stores, the potential positive feedback, which Mike spoke of earlier, between peatland carbon loss and intensifying climate change is particularly concerning. So to summarize, we have field measurements which have shown that pristine contemporary peatlands typically burn at around 1 kilogram of carbon per meter squared. When we look at the margins of those pristine peatlands, which tend to be drier, we can see 5 or even up to 20 kilograms of carbon per meter squared. Drained peatlands that have then subsequently burned can have losses of over 20 kilograms of carbon per meter squared. Although in the past we've used these drained peatlands as analogs for climate change, our modeling suggests that bogs and fens that are subjected to both warmer and drier climate conditions are going to have losses around 7 to 9 kilograms of carbon per meter squared. So again, not quite as pessimistic as a drained and burned peatland. By 2100, our model suggests that combustion losses are going to be 40 to 70% higher than they are today. And these increased losses are going to be concentrated in the Hudson Bay lowlands, the Siberian lowlands, the Canadian Boreal, and Silesia. And with that, I'd like to thank you all for listening. We'd be happy to take any questions, and keep your eyes peeled for an upcoming publication.
Thank you, Mike and Owen. That was really great. If anyone has any questions, you can post them in the chat box. Those numbers are quite astounding and a little worrisome, I have to say. And the first question, or one of the first questions that comes to my mind, is about smoke implications as well from these new sources. So I don't know if probably well outside of the wheelhouse of this research. But if you have any comments on that while I read your first question, feel free to chime in.
Yeah, the smoke is definitely concerning, and that's something that a lot of people care about across the world. I mean, the Canadian wildfire smoke made headlines, has been making headlines for the last few summers, not just in Canada. It's been ruffling feathers all over. And Yeah, this is particularly concerning for smoke generation because a lot of the smoke that comes from the recent wildfires is coming from peatlands burning. Um, and of course, it's not just smoke that gets released from peatlands burn, but they're also very excellent at holding on to all sorts of nasty contaminants. And when the peatlands burn, they release that into the air and to the water. So that's also a concern.
Thanks, Owen. Okay, so we have a first question in the chat, and I believe the question is, once peat is hydrophobic due to drought or drainage, can it be hard to turn the peat back into a moisture absorbing structure? So they're asking specifically about Northern Alberta or BC, where the bogs have been affected by drought for many years. If they do end up receiving moisture, will it take them many years to recover, or do they bounce back relatively quickly?
Now, I can take this one. That's a great comment, Raymond. We've studied this extensively in Alberta, particularly post-fire hydrophobicity and water repellency. We actually feel that it's a really important feedback for keeping the peatland wet post-fire, particularly in forested peatlands in Alberta, where the potential evapotranspiration increases with the loss of the tree cover. So the hydrophobicity actually acts as a one-way valve. You do get a little bit of infiltration, but it actually reduces evapotranspiration quite dramatically, which gives the moss some time to recover. So it's not all necessarily bad news with hydrophobicity. We don't see that in Ontario. We see the hydrophobicity breaking down much quicker in the wetter ecosystem. Now, I think what you're saying about drained peatlands is absolutely. So you could have a drained peatland or a road, particularly around an urban area where the drier portion of that peatland could become hydrophobic because of the drying, which then sets it up for potentially more vulnerability to fire.
Thanks, Mike. Really interesting dynamics there. Do you have any ideas of why it's so different between like Northern Alberta and then in Ontario, the way it's reacting?
Well, in one climate, the boreal plains of Alberta are subhumid climate compared to Ontario, which is much more humid, and also the nature of the geology, the Canadian boreal shield versus the boreal plains. So the boreal plains can be much drier than the boreal shield, and you can get much more rewetting. We can see that just on the time of the length of smoldering is much shorter on the boreal shield and the boreal plains as well. But back to Raymond's point, we've actually developed techniques similar to what Dr. Sophie Wilkinson is doing at the Pelican Mountain experimental site for trying to increase sphagnum cover after fuel treatments, as we've developed an approach to add sphagnum plugs to a peatland post-fire to increase its recovery and to break down that hydrophobicity quickly. It was actually some work done by Brandon McKinnon, who's at FP Innovations.
Very interesting. Thank you. Are you doing those manually on site, or are you able to distribute them out of aircraft, just out of curiosity?
This is just manually, but there is some work being done by Dr. Colin McCarter at Nipissing for restoring contaminated peatlands in the Sudbury region, and they have plans to do airborne sphagnum seeding, if you will. There's also a question on this chat here from Charlie about, is any of the work informing the development of peatland fire weather indices? And I'm really excited to say that Dr. Sophie Wilkinson has just developed with a bunch of others, including myself and Mike Waddington, the peat moisture code for the next generation of the Canadian Forest Fire Danger Rating System. That's currently in publication. So that consists of a new moisture code, which mimics water table position, and also has a peat smoldering index. Sorry, a peatland spread index to allow for different types of peatlands, forested, bog, and fen, etc. So stay tuned for that. It's pretty exciting.
Awesome. That is really exciting. Mike, I didn't ask your permission, but I'm assuming that you are going to share when this gets published on Blue Sky. So I'm going to share your Blue Sky handle in the chat in case anyone wants to follow that. Oh, and if you have a LinkedIn or Blue Sky or ResearcherGate that you'd like to share so that the audience can connect with you, please feel free to post that in the chat as well. To wrap up our session today, our final presenter is Sean Coogan. Sean is a researcher at Thompson Rivers University in British Columbia, and he's going to be sharing some of his work on daily lightning-caused wildfire occurrence modeling. So welcome, Sean.
Hello, everyone. Thank you, and welcome to my talk. Today, like Karen said, I'll be talking about a lightning-caused fire occurrence model for the province of British Columbia. So why predict lightning-caused fires in BC? So in BC, approximately 60% of wildfires are caused by lightning. And I did find a figure online that said about 87% in 2024. Lightning-caused fires account for the greatest area burned in the province, as well as Canada-wide. They can be very high-impact events, community evacuations, infrastructure damage, and widespread smoke. And in the past 100 years, 4 of the most extreme fire seasons have happened in the last decade. And improving upon our lightning-caused fire prediction models is critical for planning and resource allocation. So just in general, the study objectives were to develop this daily lightning-caused fire occurrence model, also to identify key drivers or predictors. Also, I wanted to characterize the spatial and seasonal patterns in predicted occurrence probability. And then also I look at a case study where I kind of evaluate and demonstrate the performance of the model. So for fire occurrence data, I used the National Burned Area Composite, which is a collection of fire burned area perimeters that's available online from the government. For the initial locations, I used polygon centroids. I used I subset to the BC agency wildfires, but I also included the Parks Canada fires that occurred within BC. And then I rasterized these fire occurrences to a common 0.1 degree analysis grid. So basically, if there was a fire in that pixel, it'd be just a single presence for that pixel. For the fire weather predictors, we actually use the ERA5 land reanalysis data, which is produced at 0.1 degree resolution. There's 4 main input variables to the FWI system with the temperature, relative humidity, wind speed, and precipitation. And we use those to calculate the fire weather index system variables, such as the FFMC, DMC, and DC. For fuel dryness, for fuel load, the buildup index. For spread, the ISI, for intensity, FWI, and suppression effort variable, the DSR. For daily lightning variables, I used the Canadian Convective Parameters and Lightning Dataset, CAN-CLPD, and it's a quality-controlled version of the Canadian Lightning Detection Network data, and it's available at, as well, 0.1 degree resolution. And when I obtained that data, it was available for 2001 to 2023. So I've subset basically all the data, that predictor data that I used, and occurrence data to that time period. I also created a lagged lightning variable. So holdover fires, basically fires that can smolder before flaming or before being detected, or delayed detection in remote areas. So the lagged lightning variable created summarized delayed occurrence probability for each pixel and for each day. So what I actually did is I used these cumulative distributions that were published in the Global Holdover Fire Database. For example, there was 2 areas in BC that they had data for. And on average, it was about 60% of fires, lightning-caused fires, were detected within 1 day. And then it stretched out to as far as 20 days, where 99% of fires were captured. So I used the 20-day period, but I created a weighted 20-day sum using the relative frequencies from the cumulative distribution function to weight. So it would emphasize recent lightning, but it would downweight older events. So for example, lightning that occurred 20 days ago would be weighted much less than lightning that occurred 1 day after. And this helped me to avoid kind of arbitrary lag selection, like maybe 3 days, maybe 5 days, or maybe including multiple variables, lag variables, and helped me to kind of create an empirically derived variable for lag lightning. I also included day of year as a predictor. So previous research as part of the network we did was looking at lightning efficiency in eco-provinces and eco-zones in Canada. And basically what we found in BC is that there was a non-linear relationship between lightning efficiency and that varied by day of year. So I included that in the model as well. One idea we had is maybe include those regression equations specifically in the model as some sort of variable. But we only had it for the lightning efficiency equations for a few eco-provinces. And so we included day of year as its own single predictor in there. I included a bunch of regular, commonly used other predictor variables. So X, Y, lat long variables, included eco-provinces in there to account for these broad ecological zones, elevation to reflect BC's highly variable terrain. For fuel layers, actually, I used the ScanFi data to make percent conifer, percent deciduous, crown closure, and vegetated fraction layers. In fact, I did experiment with using FBP fuel type layers in preliminary models, and they actually performed pretty bad. And some cases, taking those variables out actually improved the model. So I went with this approach for using the ScanFi data. So for data processing, all of the predictor layers and the occurrence data, they're all aligned to a common daily 0.1 degree grid. Each row in the data set comprised a single pixel day observation. So each pixel for each day across the entire province. For a seasonal subset, I subset to May, September. So in BC, the main lightning caused fire season is June, July, August, with most lightning caused fires occurring kind of around end of June, early August. But I also want to get these kind of shoulder months in there as well, but without extending that further, because the amount of data the model had to chunk through was actually quite significant. As I mentioned before, the yearly subset period. And the final data set actually comprised 40 million pixel day observations. So my modeling approach, I actually use a machine learning approach called XGBoost, extreme gradient boosting. So it's a very powerful and somewhat popular machine learning algorithm. One thing I really liked using this model as compared to, for say, like a logistic regression model, is that it handles nonlinear relationships. So I wouldn't have to code in, for example, quadratic variables into the model. It handles multi-collinearity, so a lot of these variables, climate variables and fire weather index variables, are correlated with each other. And it also does the interactions as well. So I wouldn't, for example, have to put FWI times day or something like that as an interaction term. It would automatically go through all those interactions. For class imbalance, so this is a rare event modeling, so it's highly imbalanced because there's relatively few lightning caused fires. Within XGBoost, it handles this by using observation level weighting of fire days. I used a training validation test split of 80-10-10. I had used 80 because we had instead of, for example, 70, because we had a lot of data to work with. Training data validation for hyperparameter tuning, and the model was evaluated on the held out test data. So model performance, the model performed pretty well. Actually, it showed strong discrimination with an AUC of 0.923. Balance accuracy was respectable. Balance accuracy is a good metric to look for these highly imbalanced data sets because it equally weights sensitivity and specificity, where sensitivity gives you an idea of the model's ability to accurately assess true positives, and specificity is to accurately for true negatives. False positive rate was 0.11, false negative rate 0.19, so respectable. The model did have low precision, and this is to be expected due to the rarity of fires. And it's got a feature of this rare event modeling. So for feature importance, I ranked feature importance based on SHAP values, and SHAP kind of gives you an idea of each variable's contribution to these pixel, the probabilities of fire occurrence. So we can see that temperature was dominant, almost doubled the next most important variable, which was the Duff moisture code, and which that result is actually well supported by the literature that shows the importance of the Duff moisture code in the lightning caused fire occurrence. I'll show you the photo again at the end of the presentation, but if you recall that at the beginning of the slide, there was an image of a lightning strike hitting a tree, and the lightning strike basically travels down the trunk of the tree and goes into the soil Duff moisture there. And that's where the lightning caused fire can kind of smolder and ignite. We also have other, day of year was actually pretty important. Other Canadian Fire Weather Index variables like the buildup index, drought code, precipitation. We can see that fuels were kind of moderately important, like with deciduous cover being less likely for lightning caused fire. Southern interior mountains was equal provinces generally weren't that important, but the southern interior mountains were seeing more activity. Lightning, the actual lightning variables, they were moderate in importance. So what we find is that while lightning is necessary like to start a lightning caused fire, there's actually a lot of lightning that doesn't cause fires. And other indices like FFMC are further down on the list. Okay, these are SHAP dependency plots, and they kind of show for the top 6 variables, and they show the relationship with that variable and in the model, right? So I kind of made 2 different figures here. One is just a subsample of the points, so it's very hard. They wouldn't plot all 40 million points, so I did a subsample of 200,000 points on the left. And then on the right-hand side, because actually getting a trend line to fit in these wasn't so simple, it wasn't tailored to the data, so I actually made these binned averages on the right-hand side, where the red dots show the actual averages per bin, and then the blue line just connects the dots to kind of get a sense of what a trend might look like. So we can see with temperature, it was actually very much a linear relationship from, say, about 6 degrees Celsius onwards. With DMC, buildup index, and drought code, we can see there's kind of a nonlinear relationship with kind of a threshold effect at a certain point. Day of year actually had a nonlinear relationship where it was more important earlier in the season. So 120 to about 153-ish is May. And then it became less important as the season went on. And for precipitation, there's actually, we can see that it basically when precipitation accompanies lightning quite often, right? So, but sometimes with dry lightning, you might expect it to be a bit more conducive to starting a fire. So we can see that most fires are occurring with, well, not most fires, but the probability is pretty high. It varies at 0, but then it kind of increases up to this interestingly is about 3, which I think is a cutoff for dry lightning, a definition, but you can see most of it's below 10 millimeters. Okay, so what does this look like in practice? So here's a predicted spatial pattern, just the mean predicted occurrence of a probability across the province. And I think that the spatial patterns do make sense with this, especially we have this period, this area up here in the northeast that we do notice gets a lot of fire activity, I think last year as well. We have the central part of the province, and here's the southern interior mountains ecozone, or eco province down in the southeast corner. And also Vancouver Island's got a little bit of a hot spot there. And these are all the 0.1 degree pixel resolution. Oops. Also seasonally, the seasonal patterns kind of just generally show in June, it seems a bit more activity up north. but then that kind of shifts to August where we see it kind of becomes more prevalent down south and on the island as well. Okay, here's a case study. So this is one case study I picked for 31st of July in 2018. So this was a high fire year. On this particular day, around this particular day, there's severe lightning storm produced tens of thousands of strikes, igniting fires, and such as the Alkali Lake complex that occurred around this time. So this is the predictions for lightning-caused fire occurrence for that day. So you can see that it's very, very high across the province from north to south. I also overlaid on this the actual locations of wildfires that occurred on that day as these red points. So you can see that generally they are corresponding with predicted high fire probabilities in the province, especially in the central and south here. However, I made a separate map that was the same predictions, but I masked out. I only included areas where lightning also occurred on that day. So we can see that there is actually a lot of good coverage here between where lightning occurred and the high probability of lightning-caused fire occurrence, and also none happening up in these low zones. Down south as well, these some little clusters, but we can see there's some clustered areas that weren't, there was no lightning predicted on that day. However, if we include that lagged lightning period as well, so the same day lightning plus lightning in the past 20 days, or about 3 weeks, we can see that the actual spatial correspondence between where lightning had occurred and had the potential to hold over and where these fires occurred on that day, recorded on that day, it aligns very nicely. So it actually shows the importance of this lagged lightning effect. And as another, this is also leads to kind of how this could be used. For example, if we take the lightning mass that we have there and say that's actually a lightning forecast instead of what lightning occurred, we could use a prediction, for example, on the left, and then use a lightning forecast. And even better to include the lightning forecast plus the previous, for example, 3 weeks of lightning. You could get a better idea of where these fires might occur. Okay, so just to summarize everything, high predictive discrimination with the rock, temperature dominant. The SHAP revealed many nonlinear threshold-like responses. The spatial seasonal maps produce known kind of occurrence patterns, seasonal structure. Like lightning, improved the spatial coherence despite modest global importance. And the framework, I think, could support early warning, preparedness, and resource prepositioning, and it can be built upon, for model for forecasting as well. So thank you, everyone. I want to thank Dante, who creates these Aero5 variables and maintains that database for us, and also Professor Mike Flanagan, my supervisor and collaborator on the project. So with that, I open up to any questions.
Thanks, Sean. That was great. Really interesting. I, as always, have many questions, but if anyone else has any, please post them in the chat box. And while we wait to see those questions come in, my first question for you is, did you look at teasing out any of the lightning characteristics, such as long continuous current, polarization, multiplicity, things like that? No,
not in this one. Just the lightning data I have is just is density, is count of strikes.
Okay, makes sense. There's a question in the chat asking if it may be better to use ignition locations from fire reports rather than the MBAC centroids and observed weather rather than Aero5.
Okay, so there is a little bit of there can be error with the polygon centroids, so that is an issue. But I don't. Yeah, that's the data I have available is the NBAC and the NFDB point database. So I don't know the other data that you're talking about there. So, but yeah, having more accurate fire ignition location would be helpful. but also it is a 10-kilometer pixel as well, so it's not super fine scale that way. Observed weather. Well, then you get into the issue of using the weather station data in the interpolation. The actual ARO5 data already does that, and it has been done by a big organization, right? That takes multiple data inputs to do this, and I think you could go either way, and I think it might be interesting to compare to see what results might be better or how they compare to each other. So I think that's an interesting question.
Yeah, you should be able to get some of that ignition location data directly from the fire management agencies. That's
Okay.
within their data set. For some, they often try to trace back to the tree or lightning strike
Yeah.
to rule out human caused.
So, okay.
Could be an interesting next step.
Yeah.
You showed a map with where you looked at lightning occurrence with day of fire. So we could go back.
Which one?
And so I was just curious on that map. I guess my first thought was like, we're showing lightning occurrence and then if a fire started, but that could be misrepresented in some ways because just because lightning occurred on that day doesn't mean that fire was caused by that lightning. It could have been a result of a holdover from a previous storm.
Yes. Yeah, I think, but I also did map with the holdovers as well. So this map shows the holdovers and the current day fire.
Okay.
So
interesting.
Yeah, so mapping at the actual ignition location is another step that could be done. But this is basically relative to the agency report date. So I assume that that's when the agency thinks that the fire has happened on that day. So it's kind of like an agency occurrence date based on that database.
Yeah, I would assume if it's a report date, it would be the day that they got it called in or spotted.
Okay, yeah. So if we had the exact lightning strike that lighted the fire, we wouldn't need the holdover period because then we would know when the fire started. Right? We would know that it didn't start previously. If that makes sense.
Yeah, really interesting, Sean. If anyone else has any questions, please feel free to post them in the chat while we wait to see if any of those come in. Good job to our presenters all for staying on time. Thank you for that. I know it's hard, and I appreciate that we were able to fit everyone in with our cushion room as accounted for at the end of the session. So I'm going to open it up for one last round of final questions for any of our presenters. So as a reminder, we had Max up first, and he was talking about optimizing air tanker dispatch. And then we had Mike Waddington and Owen talking to us about peat fires and changing climate. Then we had Shuin talking to us about novel spatial interpolation methods for FWI in Ontario. And we wrapped up with Sean talking to us about the lightning occurrence model. So if anyone has any questions, please feel free to post them in the chat. If we don't have any questions come in the next kind of 20 seconds here, we'll probably wrap up a little bit early today. And I'd like to thank everyone for coming and sticking with us. I feel like we had all of the possible technical issues today, so appreciate your patience and understanding through that. I hope you all have a wonderful weekend. And for those of you who might have missed session 1 or 2, you can find it on our YouTube channel at Canada Wildfire, YouTube at CanadaWildfire.com. This session will be posted sometime next week as well there. And so everyone is aware, we will have a final session for February flare-up coming next week. And in that session, we're going to be looking at 3 more projects. So we're going to look at wildfire containment probability is not affected by eastern spruce budworm defoliation in Ontario with Kennedy Corcola, and she's from the University of Toronto. We're going to look at the impact of spruce budworm defoliation legacies on wildfire burn severity and post-fire recovery with Jack Goldman, also from the University of Toronto. And we're going to look at terrestrial LiDAR to evaluate the gradual change in fuel structures following jack pine budworm outbreaks with Leo Jordan, also from U of T. So some great projects on insect disturbance coming out of the University of Toronto will be highlighted next week. With that, I'm going to wrap the session today. Thank you to all of our presenters. You all did wonderfully. So much information and great stuff to learn. Very thankful and appreciative. And thank you to our audience. Have a great weekend, everyone, and we hope to see you next week. Bye-bye.